Hey everyone, and welcome. Today, we're going to dive into one of the coolest and honestly most stubborn principles in all of physics. It's a law that describes this fundamental pushback in nature, almost like a magnetic inertia. All right, let's get into it. So, we're going to start with something that looks for all the world like a magic trick. This is a real photo. It's a solid metal ring just floating, actually jumping, right into the air above a coil. There are no strings, no hidden fans, nothing like that. It's just pure electromagnetism doing its thing. So that's our big question for today. What in the world is going on here? What force is so powerful that it can just overcome gravity and launch this ring into the air? Well, the answer, it's all down to a beautiful piece of physics called Lenz's law. And here's how we're going to solve this puzzle. We'll start with the main idea of this magnetic pushback. Then we'll get the official definition of Lenz's law and lay out the rules so you can predict what's going to happen. After that, we'll apply those rules to some classic examples, and finally, we'll circle all the way back to explain not just jumping rings, but also those sparks you see when you unplug stuff. Okay, let's get right to the heart of it. This whole idea isn't just about magnets attracting or repelling. It's about how they react to change. All right, so here is the formal textbook definition. I know, that's a mouthful, but the most important words in there are oppose the change. So let's break it down. Magnetic flux is just a fancy term for the amount of magnetic field passing through a loop of wire. Anytime that amount of field changes, if it gets stronger or weaker, the loop itself generates a voltage. We call that voltage an electromotive force, or EMF. Lenz's law is simply the rule that tells us which way the current is going to flow because of that voltage. And this, right here, is the core idea. You can basically think of it like this. Nature is just a little bit lazy. It likes things to stay the same. If you have a loop of wire, it gets comfortable with the amount of magnetic field passing through it. So if you try to increase that field, the loop fights back. It creates its own field to push against you. And if you try to decrease it, the loop will create a field to try and pull it back up. It always resists the change. And you know, this isn't just some random rule nature made up. It's tied directly to one of the biggest rules in physics. You can't create energy from nothing. Think about it. If the loop helped the change instead of fighting it, you could just give a magnet a tiny nudge, and the loop would pull it in, making it go faster and faster, creating its own energy out of thin air. That's a perpetual motion machine, a total free lunch, and physics says there's no such thing. This opposition makes sure you have to put work in to get energy out. So, how do we actually predict this pushback? I mean, how do we know which way it's going to go? Luckily for us, there's a clear step-by-step strategy we can use every single time. If you're studying physics or just trying to wrap your head around this next slide is your secret weapon. It's a game plan that turns what can be a really confusing problem into a simple, logical process. Okay, let's walk through this playbook. 1. Just draw what's happening. It always helps. 2. Figure out the direction of the magnetic field you're starting with, the one from the outside. 3. And this is the most important question. Is the amount of that field inside your loop getting stronger or weaker? Is the flux increasing or decreasing? 4. Based on that answer, figure out which way the loop needs to create its own magnetic field to fight that change. So if the flux is increasing, the new field points the opposite way. If it's decreasing, the new field points the same way to help it out. 5. We use a clever trick called the right-hand rule to figure out which way the current has to flow to make that new field. And finally, 6. That current is pushed along by the voltage, the EMF, that gets created. All right, enough with the theory. Let's put this playbook to the test with a couple of classic examples and see how it works in the real world. Here we go. Look at the left side. We have a north pole moving toward the loop. That means the magnetic flux pointing into the loop is increasing. To fight that, the loop needs to push back, right? So it creates its own north pole to repel the magnet. To do that, the current has to flow counterclockwise. Now look at the right. A south pole is approaching. The flux is still increasing, but this time, to repel a south pole, the loop needs to create its own south pole, and that requires a clockwise current. See? It's always about opposing the change. So how do we know which way the current needs to go? We use this awesome trick called the right-hand rule. Seriously, try this. Point the thumb of your right hand in the direction of the magnetic field you want to create. So in that first example, you'd point your thumb up. Now look at the way your fingers naturally curl around. That's it. That's the direction the current has to flow in the loop. It's a super handy shortcut. Okay, let's test ourselves with this one. A magnet is going to pass all the way through a loop. So, as the North Pole enters, the flux is increasing. The loop wants to repel it, so it creates its own North Pole, which means a counterclockwise current. Okay, what about when the magnet is perfectly centered in the loop? Well, the flux isn't really changing at that instant, so no current. Now, what about as the South Pole is leaving? The flux is now decreasing, so the loop tries to pull it back. It creates a North Pole to attract the South Pole, which means the current has to flow clockwise. The current completely reverses. So far, we've only been talking about the direction of the current, but can we actually calculate how much current there is? Oh yeah, absolutely. Let's take a look at a real problem. We've got this coil in a magnetic field that's pointing out of the screen, but it's getting weaker over time. We've got its resistance, and our mission is to find the exact value of the current flowing through it. First things first, we need an equation for the magnetic flux. Remember, flux, that's the Greek letter phi, is just the magnetic field strength, B, times the area of the loop, A. Now in this case, the field B isn't constant. The problem says it decays exponentially, described by this little function here. The area, A, is just the area of a circle, pi r squared. So we just multiply those two together, and that gives us the flux at any given moment. And now for the really key step. A principle called Faraday's law of induction tells us that the voltage, or EMF, is equal to how fast the magnetic flux is changing. And in math, the rate of change means we need to take the derivative with respect to time. So we take the derivative of our flux equation, and it spits out this expression right here. This is powerful stuff. It tells us the exact voltage in the loop at any time t. And now we're on the home stretch. This is the easy part. We have the voltage, which is the EMF, and we know the resistance of the coil, R. To find the current, we just pull out our old friend, Ohm's law. Current equals voltage divided by resistance. We plug in our equation for the EMF, and bam, there you have it. We've calculated the induced current. Okay, so we've covered the theory, we've even done the math. Let's bring this all home by looking at some really powerful, real-world effects of this magnetic pushback. Have you ever unplugged an old vacuum cleaner or a fan and seen a little spark jump across the prongs? Yup, that is Lenz's law in action. When you open that switch, the current in the coil tries to drop to zero instantly. That makes the magnetic field collapse incredibly fast, a huge change in flux. So to fight that change, the coil induces this massive voltage to try and keep the current flowing. And that voltage is strong enough to make the current literally jump through the air as a spark. And this brings us right back to where we started, with our jumping ring. When you flip that switch on, a massive magnetic flux suddenly rushes up through the ring. The ring, following Lenz's law, does everything it can to oppose this sudden change. It induces a huge current to create its own magnetic field pointing down, pushing back with everything it's got. You end up with two powerful north poles right next to each other, and they repel so violently that they launch the ring right into the air. It's not magic at all, it's just magnificent physics. So we've seen that nature has this built-in resistance to change. But this opposition, this pushback, isn't just some weird little quirk. It's the fundamental principle that powers our entire world. Every single electric generator, from a dam to a power plant, works by using mechanical energy to force magnets past coils of wire. And that magnetic resistance, that stubborn opposition from Lenz's law, is what generates the electric current that flows all the way to our homes. So the next time you flip on a light switch, just take a second to remember the elegant cosmic stubbornness that made it all happen.